Hey everybody, welcome back to Betty and Leon. Today's episode we continue with our DIY race car wiring. All dimensioned up, so let's go hand make that switch panel. First things first. Let's check and see if it's actually square. Did they cut it square? Because then we can use one of the edges. Oh, it's looking pretty good. Then we can use one of these edges as the marking off edge. So then we just have to knock, where the center of the holes are, and across this way. And then we can center punch them, and then we can drill all the holes, and it should come together pretty quick. And that is my plan. Best laid plans may not be so, but it is actually properly square. I wasn't expecting that because it is a little bit out in this direction. It's like about 0.5 millimeter different between there and there, but whatever. Good enough for the girls we date. Okay, let's get into it and mark this bad boy up and get ourselves a little panel made. Doing it old school, and I guess to be honest, that's historic motorsport for you. Is we always don't need the fancy tools. Sometimes we've got to revert back to just using your hands. All right, let's crack on. There we have it, boys. Nailed it. Something abundantly clear to me is I need a proper deburring tool, because using a big drill bit isn't the nicest finish. Okay, the big reveal. I love doing this, peeling off the layers. Let's zoom you up guys out a bit. There we go. Ooh-wee. I will end up painting this, or I've got an idea on how to make it look nice and not scratchy. But next up, I'll populate all the switches and let's see if all the holes are good and everything can be switched, because you never know. Like I said, version 1 always sucks, and then you refine it. But because we're on the timeline that we're on, version 1 might have to do. The legend, the procedure. Filming you, Roberto. You're on cam, you're in the next ep.
No.
How do you feel?
Creepy.
Look at that. Look at those fresh door trip.
Look at the back of them, aren't they?
Yeah, look at that. Let me jump in there. Oh, your shirt's pretty good. Hang on. Oh! Amazing. Looks like a real one. It actually goes with the back seat, where the back seat is. There it is.
Yeah.
Back seat bruise. Just like they did back in 71.
Yep.
Something like that. Alright.
I'm looking for.
I'll leave you to it. Roberto's out here, but fresh. New door trims and dash pad right there, looking good. It's still not pulled in a position, so you might see a few ripples in it, but they'll come out of it once we strap him down on the inside and outside. And also it sees a bit of heat and stretches and does the things in the car. The dash pad itself was not great. Race cars, we don't actually run things like that. You don't run door trims, you don't do any of that, but the historic class is that you have to do that stuff, so that's why we do it. Switch panel, Dunskies, isolator goes in there, still in the car, but I realised that I need some brackets, so we're back to 3D Printski and just punching out some brackets that have a slight adjust, so we can actually bring in the car, this guy forward or backwards, to position it properly, and then I might make some just fixed brackets, but we'll see. I even thought about having a bracket that did that, so if you ever have to fix wiring underneath, But then I thought, maybe it's more trouble than it's worth when the wiring will be sweet and we'll never have issues. So, I don't know. Like I said, V1, still work in progress, but back on this bad unit and punching it out. Hour and 4 minutes later, we'll have our first bracket and we'll test it up on one side. If that works, we'll print a second one and then on to the next thing. An hour and 4 minutes later, boom, bracket. So let's fit him up and see how it fits, because I'm hoping, I actually think that the bracket might be able to be reduced a bit. Oops, we've already got a screw in there. I actually think that we can reduce the screw a touch. So where are we? About there. And I'll also print the next one. It'll have a it'll actually have a hole in the bracket for where it's going to go through here, and I'm thinking I'm going to line the screw up probably with the bottom one there, or maybe the top, depending. Noting that it's going to vibrate and do strange things. But how mint is that? Look at that. We can have him out. We can have him pointed to the driver. We can have him back in. So he's sitting flush. I did do some crude measurements and it looks like they've come out freaking awesome, because look at that. That's how we want him. He's got to sit a little bit proud because I've got to be able to reach it from the seat, but look at that. How good is that? I think I'm going to leave the bracket that size and punch a hole in the next one. I'll print 2 at a time this time. And what do we got over here? Oh man, I reckon that's going to go close, lads, to actually being able to use the hole that's in there. I'm not expecting it to be perfectly in the middle, simply because, like I said, we need it close to the driver. But how good's that? I know I like symmetry, but maybe we don't go with symmetry for this one. Where is that? Oh, there's a few holes in there, so we can pick and choose underneath what we go for. The lighting is terrible, but all right. Let me go print another couple. Then we can knock a hole in this sheet and mount him up. I'm stoked, boys. I'm really happy with that. Awesome. Fresh off the printer, we now have slidey bracket, holes in slidey bracket. So now I need to grab this unit here. I'm just going to knock some holes in it, the final holes. So the way that this sits, and let's see if I can prop this up here. So this goes obviously on the back side, but it sits like this. So you can see that the 2 holes, that's not sitting in the perfect spot, hang on. The 2 holes for the screws, which will use a button head screw, will go there and there, and they'll line up with the lights and the switch. So it'll all look uniform, be nice and held tight, and get us where we need to go. I'm pretty happy with how it's turned out, to be honest. Yeah. All right, let's fit it, and then we can move on to some actual wiring, finally. The center console, I just mounted it just to make sure that we can get it in and out as required, so it won't smash into that. I'm actually kind of liking the slots that I put in it, because I think I'm actually going to angle it a bit more, like pivot it towards me this way, because it just means it's easier to reach everything. But I'll see, because maybe I can reach everything when it's flush, and you know, flush is going to look better, but you know, it's kind of cool as well. And I was thinking maybe I can make a nice little 3D printed plate, 3D printed plate that's bolts into the top of here or something, or clips on that edge and covers that gap. But I mean, you know, it's all looking pretty damn sweet. How about that little dash pad looking nice? I need some more screws, but yeah, Looking heaps better than the old one, as are the new vents, and our little AFR gauge mounted. So yeah, it's actually looking pretty good. I think we're running out of time though, but that be how it do. I'd rather it be right than just to rush it through and, you know, not do a good job. As an interim measure, what I've done is just wrapped this and then cut it out. So instead of looking shiny in the car, it'll look matte black and sort of fit in a little bit. Because again, I don't know how long it'll be between, you know, doing this sort of interim switch panel and then getting the finalized one and having it powder coated and do all the rest. So looks pretty good, I think. Throw the switches back in it and then we can put it back in the car and actually start wiring some stuff up. And boom, now the switches are in. The handprints do wipe off, so we're all good there. I've also wired up the grounds for the LEDs for all the switches. All of your red wires there will go to the switch side, which doesn't have power when it's off, and the red one in the middle, so above the big switch there, will go to our alternator light. So we've got to supply 12 volts to the red guy, and then the black wire will go off to the switch side in the alternator. But while I was doing this, I was just thinking about explaining the difference between an LED and a globe, because I don't feel like people often grasp that, and they wonder why they try and wire it up and it doesn't work. So let's quickly go to the whiteboard and I'll give us a super quick explanation on that. Quickly drawn it up. So LEDs at the top here, normal sort of bulb / globe, whatever you want to call that. So in simple terms, LEDs have a positive side, negative side. Anode, cathode, that's what they say. Fancy names for positive, negative. The easy way I remember it is that if you're looking at a schematic, this line here is kind of looking like a negative. So you can go, okay, that's the negative side. Positive side's the opposite side. Simple, easy way to do it. They have to be connected up. If we want this to, what they say, forward bias, we need to basically put positive voltage obviously on the positive side, have a negative on the other side, and then we get lighting up. Pretty simple. So basically they can only go in the circuit one way. If you put them in the wrong way, they will not turn on. Simple as that. Bulbs, globes, they don't have a positive or negative. They can be around either way. So yeah, that's why it doesn't matter really which way you wire them. You'll always get it to illuminate. LEDs as well, looking at them, they kind of look like this. They do a few things to make them identifiable. So in a diode that's in a circuit, they have basically a white, so it looks like this, and they have like a white stripe which denotes the negative side, and then the positive. Actually looking at an LED, there's one side that looks like it's got kind of like a little flag. That's the negative side. On the positive side also, they have, if they're fresh from the manufacturer, they'll actually have a longer leg. So you can just identify it by the longer leg. So yeah, interesting. LEDs, you'll say, why use LEDs over a globe? A globe has to have a filament in a vacuum to work. It has that little, it has like a little coiled piece of wire that gets heated up, and that's what makes the light, right? We're converting electrical energy into heat and light energy. In an LED, similar sort of concept, but it's a semiconductor. So it has certain materials that, basically when current flows, creates, again, heat and light. But the difference with an LED is they're a lot more, they're MTBF. So this is a term used quite frequently in things. Mean time between failure. That means how long between failures. And I'm just going to throw some figures out there. Don't know if they're correct, so feel free to go on the web and search them up. But an LED's MTBF might be 10,000 hours. So that basically means you're going to get 10,000 hours out of that LED, generally speaking. before you've got to replace it, before it blows up, dies, whatever. You know, a globe might have 5,000 hours MTBF, which means that, you know, you can have one LED for 2 globes, say. All these things are worked out. There's a lot of math behind it. You don't really need to know about it, but, you know, that's why LEDs have sort of become probably the norm now. And also, they're a lower current draw, which is really critical, especially if you're doing some sort of lightweight harness. LEDs use less current, which then means you can use less, you know, smaller wiring to drive the LED, which then means you can save weight. So you can sort of see how that, I guess, the progression of, you know, why you would select an LED over a globe. In our instance here, we still have to remain with globes for headlights and things, so that be how it do. And you guys know, Series 1 RX2 headlights, very hard to come by. Yeah, and I don't know what to say about that. It's a bit ridiculous how much they're worth at the moment. Like, if anyone's got some, hit me up, because I do need some. I just realised on Leon he's got a blown right-hand headlight, so yep, I'm up for buying some, but yeah, super expensive. I was thinking maybe we can do some sort of conversion so we can kind of cut the the backside out of the sealed beam, and maybe make a little mount where we can put in a, you know, a new school LED or halogen or something to achieve the same outcome, because I really can't afford to just keep replacing them, even though the rules say headlights need to work. So yeah, that's one of the weird things about RX2, is a bit hard to come by, and yeah, I mean, we'll just work our way around it if we have to do that. Okay, next I'm on to putting the switch panel. So it's looking pretty cool. Let's throw this back in the car, and I'm going to leave this side off so that I can actually pivot it in the car, so then we can work on the back side and run all the wires to the switches. I just had a little thought for consistency's sake. Where's my pen at? Pen's here. So on the switches, say this is the back side, we've got a tang here with a screw through it, and we've got one here with a screw through it. For consistency's sake, what I'm going to do is bring all the plus 12 volts, like so all the switching, like the power, to the top stud, and all the bottom studs will be to the loads, whether that's, you know, a relay or actually something like a water pump or whatever else it is. I'm going to do that because then when I'm troubleshooting, I know that this is always the load side, this is always the power side whenever I'm looking at a switch. A little bit different for the indicator circuit. Indicator on the back has basically 3. We're going to feed the center, so that's plus 12, and then this is, you know, your right side indicator, this is your left on the switch. So again, keeping consistency. Just managed to get, it's a bit dark in here, where's the light? Where's the light, boys? Where's the light? Hang on, where did my light go? Don't even know where it went. Oh, just in here in the engine bay, still on. That's helpful. Like he's got some new baddies. Alright, so hopefully we can kind of see in there now without glare. A little bit of glare. That's better. So now I've got the starter solenoid has come through, goes to the back of our engine start switch, and then off the back of the engine start switch we're coming over to where we're going to get power for the fuse box. So I'm just leaving them about this long at the moment, and I'm just throwing on the, hang on, just throwing on our little heat shrinky labels. Yeah, this one here is the ground for the LEDs at the moment. So the next one I'm going to work on is actually our switch. So accessories bus switch. It basically just goes through the switch over to here. So that's another 2 cables. 22 AWG will be that bad boy. I'm also thinking maybe I need to just temporary mount the battery, just so we kind of get some holes drilled in the right spots. Then I can actually start testing some of the circuits as I finish them, because what I'm trying to achieve here is getting the start, accessory switch and alternator circuits done, and then I can actually like turn buses on and off, and we can then power things and then test them as we go, and save time as we roll through. But that's the current status there. I wasn't going to use a lot of 22 gauge, but I'm running out of, I didn't really get too much 20 gauge. So here I sit trying to work out things. Yeah, is what it is. So that switch in there will run through here, and then one side of this runs the ground. One side of this is powered from, F1 or whatever the fuse is. So to complete the circuit. Next up, let's speak about the ISO switch, because that's where we're at. The ISO switch has 3 sets of contacts in it. The first being the main battery. So what I'm going to do is draw this in the off position first. Let's talk about that, and then how it acts when you turn it on. Okay, so we have battery, plus 12 volts here. All of your loads currently open because it's in the off position. We then have another one that goes to our alternator through a resistor. I think it's about 3 ohms, and then to ground. So the purpose of this is that when you're switching from on to off, you close this circuit, and what is in the field current basically goes to earth. And why it does that is so that the alternator is not supplying power to the rest of the electrical system. So you're basically not only cutting the load, the main load off through the battery, but you're also shorting the alternator essentially to earth. That's why the resistance is so small, 3 ohms. And then we also have the ignition circuit. And the ignition circuit's kind of like a bit of a loop. It's actually in series with the ignition. So when it's in the off position, obviously it's closed, ignition won't work, fine, because we have no battery either. When we go on, all of these states change, right? So we go from being to that, because obviously we don't want to have an alternator shorting while we're on, and we also close this. So from a load perspective, we have the plus 12 volts will feed our car, so we're running, the alternator's open, so we're not shorting the alternator ground. It's actually acting like an alternator and feeding back into the battery circuit and replenishing the battery. And the ignition is obviously now got a closed circuit. When we go again off, we would open up that guy, so we lose battery. We short this to earth, so the battery power of the alternator now goes directly to earth. And we also open up the ignition, so the ignition gets cut. So that's a typical, what they say, FIA, wiring setup. Generally speaking, for motorsport, that's the basics you got to follow. They do some solid state stuff now, where you can do away with the isolator switch, and you got like a little button you can press, and it does it in a solid state way. But this is the sort of basic what you'll see in, I'm going to say 95% of cars these days, until that semiconductor solid state stuff gets cheap enough, because it's quite expensive for what it does, and these things are about $50-$60. Something I haven't really discussed yet is some of the test equipment. So this guy here, digital multimeter. This is just a cheapie from JCar. You can buy more expensive ones from Fluke and other decent manufacturers. When troubleshooting, the main ones you're going to use are volts. So you got a V, right? V with a straight and dashed line. That is the symbol for direct current, which is what a battery produces, or a power supply that's taking AC to DC. DC volts is another name. Yep. This guy here, AC, alternating waveform. Maybe I should draw that on the board as well. Kicking off with the DC. So this is what we have in our cars. Obviously we have batteries. Batteries produce DC. Generally speaking, it's plus 12 volts of DC. If we're expressing that on a oscilloscope, which is another piece of equipment that essentially draws waveforms, we would have a 0 volt, we'd have the plus 12 volt, and we'd have a line when we connect our probe up and onto the 12 volts. When we remove that voltage, we'll actually see it come down and it will go back to 0. So they call that a square wave. In automotive applications, you know, you have your batteries, of course, and you can have some power supplies that are going to convert that AC to DC. AC is the other style. Alternating current. Alternating current is expressed in a waveform that's a sine wave like this. And essentially, the component on our car that produces AC is the alternator, hence the name alternator. Alternating current, alternator, all makes sense, right? You're going to say to me, well, how do I get from an alternating current to a DC? Well, in those alternators, they have a pretty cool thing. Back in the day, it used to be mechanical, but they came up with some genius came up with the bridge rectifier. And what we have is our diodes back again. And let's see if I can do it justice by drawing it correctly. But what our bridge rectifier allows us to do is we can input the AC, and on the output we actually come out with a square wave, 0, 12 volts, you know, DC voltage essentially. So essentially what we're doing is we're removing all of the negative and we're keeping the positive side, and we're only chopping the bits that we need through using those diodes. So we end up with a pulse DC on the output, which then feeds our battery, which our battery can actually act as a capacitor. So that's why you don't see the choppiness in the automotive application, because the battery is basically is a storage device. We're topping that up. It keeps it as though it's a straight line. That's why you don't see this all the time. So it's feeding that. So that's a very basic, quick explanation on AC and DC volts in the automotive application. But this thing over here allows you to read those. Super handy. Always DC, generally speaking, unless you've got some sort of funky setup in your four-wheel drive. The next thing that we really use is ohms. So that's measuring resistance. Like a good example is our resistor right here. I'm just going to have to rest them here and hope that I can do this. Hang on. Yep, that one. When I touch this here, oh, come on, mate. Come on, mate. Oh, hang on, boys, hang on. Okay, let's try this. Try this again. Stay there, fella. All right. So when we touch this, we'll get 3 ohms. There we go. It's 3.2 ohms. 3.3. Yeah, you just got to make sure that you do that. You also will, because like I said, there's resistance in the cables, right? If you put both of your leads together, so I'm holding them metal to metal, you will actually end up with some resistance, right? Because we did say earlier in the game that the cables have resistance per foot, per meter. Just proved it for you. Other items in here, hertz, pretty good for measuring a frequency. Hertz is a measure of frequency per second. So 1 hertz is something that's happening 1 time per second. 1000 hertz or 1k hertz, is 1000 times per second, so on and so forth. Pretty simples. Current is measured through your amp meter, and it's a little bit different. You've got to set up your leads to plug into the amp side of your meter, and you'll see that it's fused there. It will only have a certain size fuse, so 10 amps. If you exceed that, you'll blow up the internal fuse. You'll wonder why your amps isn't reading. Just be mindful of that if you're playing around with amps. Amp meters have to be in line with the circuit, so you basically have to break it and put it in series with the circuit, because voltage measures potential difference. You're measuring with reference to something, and more often than not in your car it's with reference to ground, so that's why you're going between ground and something to see what the voltage is. That's a quick, very quick rundown on multimeters. Oh yeah, and they got lights too, which is super handy. You've got hold functions, ranging, a whole bunch of other stuff, but yeah, great tool to have. I just run a cheapie in the race kit because if it ever got stolen, I'd cry if my fluke went missing. But yeah, a good tool to have on hand, especially when you're fault finding electrical stuff. I don't think you can do it without it. I mean, a test light works. That's a bit old school, but yep, get yourself a cheap meter. There we have it. We've got there we go. Nice little dude. I put a big chunk of heat shrink around it so that the pins don't bend. And yeah, it joins onto our little switchy dude there. This guy's there. I've gone and added a whole bunch more wires as well. So we've now got stuff coming in through the engine bay. And starting to get sensors, so oil pressure sensor, water temp sensor, so you can see it at the back of there, water tempy, and I need a 1.8 MPT fitting off the back of here for the oil pressure to work, but that's fine. I can run the cable. I'm just doing cable lengths at the moment, so that what I can do in here, and I'll do the coils next, is just running the cables to all the various sensors and things that need power. Your igniters kind of come off your coils, and I'll go through that circuit in a minute, but getting lengths and stuff, so then I can get everything protected, and then we can work on the inside. So then I'll go back to actually producing the fuse box and all sorts of stuff. I'm just trying to get the stuff that makes the car run in here first, and then we can wire them up. But yeah, it's a bit of a trying to group like terms as far as getting the, we're trying to get the everything in the engine bay into under the dash. Then once it's under the dash, it's just a case of re-terminating everything into those fuse boxes, the relays, the fuse sections for your alternator and the main fuses, all sorts of jazz. So it'll just make life easier, because then we know where the looms run, and then it's just a case of terminating. The other things that need to happen are we've got to run wires down to the back tail lights, fuel pump, and out the front to indicators, headlights, fan. So that's a different kind of loom. It goes out the side of the car, like the right hand side, driver's side. There's a firewall grommet that goes out there and sort of runs along and then runs across the front of the car. So doing that later, trying to get the car to the point where it can start, turn on, run, fuel pumps, all that sort of stuff. Focusing on getting the car running first, and then we'll focus on the other bits. But it all sort of will come together at any one time. It's a bit messy up until that point, but as long as you label things, put a piece of tape on it, do whatever you need to do to identify what the cable is, know where it's going to run, then yeah, it all comes together nicely in the end. All right, so what I'm going to do next is the ignition cables. So let's go to the whiteboard and learn about ignition systems. Let's leave it there for that one. Progress is progress. We'll see you on the next one.